Okay, video keys. So we're going to do video keys for these three energy conservation and power assignments. Um, One thing about the WebAssign stuff is that anything that you see on the screen that is highlighted in red, that's a variable number, and so every student is going to get um, a different number value substituted in that place. So for that reason, it doesn't necessarily make sense for me to solve all of these problems all the way through and like calculate final values of answers. So instead, I'll be solving the problems um, qualitatively using the equations, and then you can substitute your own numbers in uh, when you're working on your version of it, and then check your answers via WebAssign when you submit them. So that's the game plan here. And without further ado, let's get started. So here we have a block that's placed on a light vertical spring with a given force constant or spring constant, 4,950 Newton meters in this case. And it's pushed down so that the spring is compressed by 0.106 meters. After it's released, it travels upwards and leaves the spring. To what maximum height above the point of release does it rise? So what we're going to do here is, and I always like to do this but I especially like to do it with energy problems, is diagram this out. So let's say that my spring um, unloaded has this initial position. The loaded spring is going to be compressed this amount. So here's my block placed on my spring. And this original position here is X for the spring, right? So that's going to be the compressed length. That's going to be my X. Compressed length there. So that's my compressed length. So in this case, I'm given X as a given value or a known value. So we have X is given, the mass is given, the spring constant is given, okay? And then in the end situation here, my spring is not going to be compressed anymore. My spring is now released, but my block is now at some maximum height. And one thing that's important to note is that at that maximum height, the velocity of the block is going to be equal to 0. So I know the final velocity of the block as well at the highest point. And what I'm asked to solve for here is this value, this h, final. So in order to simplify this, let's define the starting position, h equals 0, so that initially my block has no gravitational potential energy. Now, one of the things that I said in the description for this problem set is that all of these are conservative forces. Conservative forces. And what that means is that energy is truly conserved in this problem. So the initial energy is equal to the final energy within the system. So that makes this pretty simple because at the beginning, my initial energy is going to be only spring energy, right? Because I defined that initial height as height 0, meaning that it won't have any gravitational potential energy. And it's not moving, so it has no kinetic energy. So U spring initial is going to be equal to my final energy. In the final condition, that final energy is just UG, gravitational potential energy. Because again, the spring's no longer compressed, so there's no spring energy. And at its highest point, it's not moving, so there's no kinetic energy. And so then substituting in here becomes pretty straightforward. I can just substitute in my spring potential energy equation, 1/2 kx squared. That's going to be x initial equals my UG at the end, MGH final. And the problem asks for that final height. So solving for height, you'd get kx squared over 2mg. And that should be your solution when you just plug your numbers into that and you get an answer out at the end. So that's that first problem there. Moving on to the second problem, I'm happy about this because I already have a diagram drawn. So again, let's start off with reading the problem and knowing our givens. Two objects are connected by a light string. That means that the string itself has no relevant mass. Passes over a frictionless pulley, so we have no outside forces here. Again, because it's frictionless, this is likely to be conservative forces. The object of M1, so my given, I know M1 as a given. I know that it's released from an initial height. So I know H naught for M1. And then below, it asks me to determine the speed of object mass M2 just as the M1 object hits the table. So M2 is also a given value here. And the starting height of M2 is also known. We'll define that as height 0. So for this part of the problem, what's happening is my initial will have block M1 up at some initial height, not moving, block M2 at height 0, not moving. My final will have their positions reversed, but they will also both be moving. In this truly conservative problem, E naught is going to be equal to E because there are no outside forces interacting with my system. So the initial energy here is just going to be gravitational. And because none of them are moving yet, and because block M2 is at height 0, it also has no initial gravitational energy. So my initial energy is just going to be the gravitational energy of block M1. And my final energy, three things will be happening. I will have a gravitational energy for block M2 because M2 will now be above the table. And I will have the kinetic energy for both blocks. You could combine these two kinetic energies because they'll be moving at the same velocity, the same speed. So you could actually just call this the kinetic energy of block M1 plus M2, and that would work as well. So once I have this, my problem is pretty straightforward, right? I have M1 times G times H for my initial equals M2 times G times H for my final gravitational energy plus 1/2 times M1 V squared plus 1/2 times M2 V squared. Simplifying this a little bit, it would be M1 GH minus M2 GH equals 1/2 M1 V squared plus 1/2 M2 V squared. And then, like I suggested just a second ago, because the velocity of each block is the same, or rather the speed is the same, the direction's opposite, but the direction doesn't matter because it's being squared, we can simplify this term on the right side as well. So this would be M1 minus M2 GH equals 1/2 M1 plus M2 V squared. And then our goal here is to solve for that velocity. So that velocity is going to be, simplifying this further, 2 times m1 minus m2 times gh all over m1 plus m2 equals v squared, and v will be the square root of this value on the left side. So there's my final answer for part A of this problem. Part B of this problem says, what's the maximum height that block M2 rises? So for part B, I guess I should write this down. This is part A. For part B, the new question is, my block M2 has some initial velocity at some height h. That we solved for that velocity in the previous problem. And then when block M2 is at its highest point, it'll be at some new height, a final height, and its velocity will be 0. So this is, again, true conservative forces because there's no outside forces acting on it outside the system being the block and the Earth. So I can say the initial gravitational energy and kinetic energy of this block is going to be equal to the final gravitational energy of this block. So that initial gravitational energy will be m2 times g times h, where h is from the previous problem. H is this h given. And then that'll be plus 1/2 m2 v squared, where that v is solved for here in part A. And that's going to be equal to m2 times g times h final, or the maximum height. Again, you could cancel the h's out here. So let's do that. Cancel, cancel, cancel. And we would get gh plus 1/2 v squared equals gh final. And we could simplify this further to 2gh plus v squared over g equals h final. That's the maximum height there. That would be the end of our problem. Moving on, for this third problem here, we have 2 cannonballs, one that's fired at an angle and one that's fired vertically. So again, I like being able to diagram these things. So cannonball 1 is fired with an initial velocity at an angle of 40 degrees. Let's call it theta. The other one is launched vertically with the same initial velocity, and that's fired at 90 degrees, so vertically. We're defining position 0 as the position at which it leaves the cannon. So for the first part of this question, we're asked to find the maximum height reached by each ball. You can solve for this using solely using kinematics and free fall equations, which is fine, and that'll get you the right answers. It does say to use the isolated system model, so it's asking you to use energy in this. And that's an example like on the AP exam. If they ask you to use energy and you use kinematics, they're not going to give you credit for that because you haven't answered the question that they've asked. So in this case, we'll use energy. So key here is that at the highest point, each ball will have a vertical velocity of 0. So Vy equals 0 for both balls. But for the ball that's fired at an angle, Vx is not equal to 0. So it is moving horizontally at that position. So the ball that's fired vertically is very easy to do. For the ball that's fired vertically, second ball, we just have kinetic energy at the beginning is equal to gravitational energy at the end. So we have 1/2 mv squared equals mgh, and h max is equal to v squared over 2mg. So that's pretty easy. For the one that's fired at an angle, it's a little bit different because the ball will still be moving at its highest point. So if we really want to use the isolated energy model in its entirety, then we would set it up this way. We would say the kinetic energy at the beginning is going to be equal to the gravitational at the end plus the kinetic energy at the end, where the kinetic energy at the beginning is 1/2 mv squared. The gravitational energy at the end is m times g times h max, the maximum height. And the kinetic energy at the end is 1/2 m v squared for the end. Now, I know my initial velocity and I know my mass, although the mass cancels in this equation. What I don't know here is what the final velocity of the ball is going to be when it's launched at this angle. That I have to go back to projectile motion for. And so in this case, going back to projectile motion, this v is v in the x direction, which is v naught times cosine of theta. So that's all. I can substitute that into my equation. Canceling the masses here. I get 1/2 v naught squared equals gh max plus 1/2 times v naught cosine theta squared. And then solving for h max. So you'd have 1/2 times v naught squared minus v naught cosine theta squared divided by g equals my h max. And that's that. So here's my answer for the vertical one. Here's my answer for the horizontal one. Now, the second part gets even easier, actually, because it asks for the total mechanical energy at maximum height for each ball. So for this part, for part B of this, it's actually just asking for like one side of this equation, right? So for part B, it's saying, what's the total mechanical energy? Well, let's take the ball that's fired at an angle, which is the complicated one, right? The ball that's fired at an angle, the total energy, that's not how you spell total. At max height. Well, for ball one, that would be the gravitational potential energy at max height plus the kinetic energy at max height. Effectively, it's saying it's this value, right? UG plus K. Well, if I'm paying attention, I actually know that that is equal to the initial kinetic energy anyway, right? And so I don't actually need to solve for UG plus K. All I really need to solve for is K initial. And K initial is super easy. K initial is just 1/2 mv naught squared. So that would be my total energy. And because both balls start with the same gravitational energy of 0, then both balls have the same initial kinetic energy and the same total energy. So that's actually my answer for both parts of this problem. The total energy is going to be equal to 1/2 mass times the initial velocity squared. Done. Okay, continuing on. For this one, we have this light, rigid rod. Light, again, meaning that the rod itself is massless. And its top end is pivoted on a frictionless axle. So what the frictionless tells me is no external forces. This will be a truly conservative system. Initially, it hangs down with a ball attached at the bottom end. So here's my initial situation is I have the rod hanging down with a ball attached at the bottom. And the ball is struck so that it's given a horizontal velocity and it swings around in a circle. What's the minimum speed at the bottom required to make it go all the way around in this circle? So at the end, it's going to be at this height here. Now, minimum speed at the bottom to just go over the top of the circle. What that over the top of the circle means is that V at the top is effectively 0, right? I know that in order to go over the top, it has to be moving still. But how much more than 0 does it have to be moving? It has to be moving infinitely small amount more than 0. So 0.000000001, right? All those zeros. Effectively, that's a velocity at the top of 0. So really, this problem is saying, truly conservative, the energy at the beginning is equal to the energy at the end. And the beginning, it will have kinetic energy, and at the end, it will have gravitational energy. What I know in this problem is the length of this rod is L. Let's define this initial position as height 0. Then my final position, the final height is going to be equal to 2 times the length of the rod. So then it's just 1/2 times the mass of the ball times its initial velocity squared equals the mass of the ball times g times the height at the end. Mass cancels here, so I get 1/2 v initial squared equals m times 2l. And v initial equals the square root of ml. Actually, it's just ml, huh? Because those, no, 4ml. Boom, done. Pretty straightforward problem. And then last but not least, we have this slide problem. We need to determine the speeds at point B and C. For starters, we know that it's a frictionless track, and we know that initial height. So h naught is a given. This is, again, a pretty straightforward problem. Given that it's frictionless, we now have a truly conservative system. So at point for each part of this, my initial energy is going to be equal to my final energy. And for points B and C, I will have both movement and gravitational energy. At point A, I only have gravitational energy. So I have UG initial is equal to UG final plus K for each of these points. So for point B, that is UG initial is going to be m times g times the height of A equals 1/2 m times v squared at point B plus m times g times the height at B. Solving for velocity there, mass cancels out, and I get v equals the square root of g times HA minus HB over, 2g, and that's it, right? mg HA minus HB times c, yep, square root of that. And then for point C, it would be the same setup, but my v would be the square root of 2g HA minus HC. It's a pretty straightforward problem there. For the last part, it's determine the net work done by the gravitational force as it moves from point A to point C. So the net work done, this is part A, this is part B. Net work done by gravity. Two ways you could solve that, right? You could say that's going to be the force of gravity times delta x in the y direction, which is effectively just the change in GPE. Or you could say that that work is going to be equal to the change in kinetic energy. And that change in kinetic energy is probably the easier way to do this. So the net work at point B is going to be equal to 1/2 times m times VB squared. Well, I already know VB, right? I solved for it in my previous problem. So you can plug that in and simplify this. And then my work at C is going to be 1/2 m times VC squared. And you're done. So that's this whole first problem set. Enjoy.